minimizing finite state machines. Finite state machines. And what this means is that we're going to take a DFA, let's call it D, which may have many states, and we're going to create from it a DFA that might be smaller, have fewer states. Okay, DFA with fewer states. And in fact, we're going to be able to construct the DFA that has the minimum possible number of states over all DFAs that recognize the same language that this DFA does. So minimize the number of states. And so we're going to end up with a DFA, call it D prime, where the language that's recognized by D and the language that's recognized by D prime is the same, but D prime will have the fewest possible number of states of any DFA that recognizes this language. Now this result, we'll do this algorithmically, will show that this is possible to do efficiently with an efficient algorithm, and we'll also show that the DFA that minimizes the number of states is in fact unique. There is only one, exactly one. And this result is actually a very useful one. It not only tells you something interesting about DFAs and what different kinds of DFAs can recognize the same language, but it's also practical. It's something that actually people want to do. There are many problems that are solved by setting up a DFA, casting your problem as a language recognition problem over regular languages, setting up a DFA, and then minimizing the number of states because you really want a very efficient and small DFA, or at least the smallest one possible. Now, the book, CIPSR, that we've been using doesn't talk about minimizing finite state machines. It's something that's often included in courses like this and in books like CIPSR. I don't know why he chose not to include that material, but we definitely want to talk about it in this class. So you'll have this lecture on video to be able to look at. And I will place on the class website I've written some notes here about 9 or so pages on this lecture, on this material, and so you can look at that material as well. Okay, so over here is an example of a DFA that we're going to use throughout the lecture, and we'll end up on that board, perhaps way down there, on the DFA that accepts the same language, recognizes the same language as this does, but with fewer states. It's the minimum sized DFA, the DFA that minimizes the number of states, overall DFAs that recognize that language. Okay, so to begin, I need some definitions, and the two critical definitions are the following. Two states in, I'll give them a name, Q and Q prime in a DFA. Now this DFA is now going to be called M. Those two states are called distinguishable. Okay, distinguishable if there is some string W from the alphabet. It's a string of characters from the alphabet in sigma star, such that if we start Q if we start in state Q and then we see the computation that's done, we execute the computation in the DFA from state Q, but using string W. So Q on W leads to a final state, final or except state, while Q prime on W, same W, does not lead to a final state. Does not end in a final state. So two states Q and Q prime are distinguishable and they're distinguishable by some particular string W. They're distinguishable if there is some string W such that if you start in state Q in the DFA M and then you do the executions following string W, then you end up in a final state. But if you start in Q prime and also do the executions based on W, same string W, you end up in a state that is not a final state. Okay, this does not lead to a final state. And that's what it means to be distinguishable. Okay, so for example, if we go over here, looking at our big example here, let's take two states A and B. So Q, let's say, is A, and Q prime is B. So we have two states. Well, actually, in order to be exactly in conformity with this definition, I want to reverse who is going to play the role of Q and who is going to be Q prime. Okay? So this is state B and this is state A. And the W is going to be, now W, let's just W is equal to 1. Okay? Now, what we see is if we start in B and we do the computation based on W, W in this case is just the string 1, then it goes over to C, state C, which is a final state. But if you start in A and you take, you do a computation based on string W, which is just 1, then you go to F, which is a not final state. And therefore, states B and A are distinguishable, and they're distinguished by this string, the simple string 1. Now, you could have also done it the following way. You could have taken the string 0, 1, I think. Let's see what happens there. And then if you started in A, you go 0, 1, and you end up in a final state. But if you start in B, you go 0 and 1, and you end up in a state that's not a final state. This is just, again, another way of showing, in particular, that states A and B are distinguishable. In this case, they're distinguished by this string 0, 1. Okay, so in this example, states A and B are distinguishable, and we could find other states in here that are distinguishable. To show that two states are distinguishable, you just have to come up with a W, a string W, that really shows that W distinguishes those two states. To show that two states are not distinguishable is a more difficult task, because that has to show that there are no strings. There is no string W which would distinguish the two states. But nonetheless, we can talk about whether two states are distinguishable or not distinguishable, even though it may be more difficult to establish that two states are not distinguishable. But we'll see how to do that. And since I've been using that term, let me just do it explicitly. Definition: two states are indistinguishable if they are not distinguishable. Okay? Which in particular means, I could elaborate on this, it means there is no string W which distinguishes the two states. If I call these states Q and Q prime, there is no string W that distinguishes Q and Q prime. Okay, so those are the two initial key definitions, what it means for two states to be distinguishable, what it means for two states to be indistinguishable. Okay, now I want to make a key observation which will be used in minimizing, in the logic of minimizing a DFA to have fewer states, and it'll be a key element in the algorithm that does this. If two states, let's say Q and Q prime, are distinguishable, are indistinguishable, however you spell it, indistinguishable. If two states are indistinguishable, then we can effectively merge those two, merge Q and Q prime into a single state in a particular way that I'll describe in a minute, so that the new DFA recognizes exactly the same language as the original DFA. If they're indistinguishable, then Q and Q prime can be merged and merged together. And the way we'll do that is the following. I'll just explain this by picture. Here we have Q prime, and here we have Q. And in these examples, in the way I'm discussing this, we're just assuming we have a binary alphabet, but the basic ideas will work for any alphabet. So let's just say we have some arrows coming into Q prime, into state Q prime, and we have some that are leaving, and this goes to, let's say, Q7, Q9. All right. Well, that looks too much like another Q. Call it Q10. All right. So we have that. And then over Q, we have its in edges, whatever they happen to be, and then its out edges. Okay. And now let's also name where these come from. Let's say this comes from Q3, Q11, Q17. Something like that. Okay? Now, we've said Q and Q prime are indistinguishable. And that should allow us to merge the two states. So what we're going to do when we merge those two states is we're going to take all of the edges that come into Q1, to Q prime, all the edges that come into Q prime, and move them over to come into Q. So this one from Q17, instead of going to Q prime, it'll go over to Q, exactly on the same character that was used. I think this was a 1 over there. Same character on that edge. Similarly, Q11 will now, instead of going into Q prime, will go into Q. And Q3, instead of going into Q prime, will go into Q on a 0. Okay? And then we're going to you just remove Q prime and the edges, not the states it went to, but the edges out of it. Okay? So that's the operation of merging on this particular little example. And let me give you a more general definition of what it means to merge, and then a claim that the merged DFA accepts exactly the same language as the original one did. So, okay. So a more formal definition of merging. What does that mean? For every edge into Q prime, redirect it to go into Q. That's the first thing we do. And then, now this is hard to read, I know. It was a semicolon. Now make it a dash. This chalk is awful. Then remove Q prime and all edges out of it. Okay? Now, we started with two states, Q and Q prime, that are indistinguishable, and we're merging them. And now in the definition of what merging means, or in the formal explanation for what merging means, we're removing all the edges, or we're redirecting all the edges that went into Q prime to go into Q. Well, which of these two states is Q prime and which is Q? It doesn't really matter. It's just that we have two states that are indistinguishable, and one I'm calling Q and one I'm calling Q prime, and then for the purpose of being specific, being concrete of how you actually merge them, we're going to redirect the edges that went into Q prime into Q, but I could have done it the other way around as well. So logically, it's the same thing. Now, we have a clear idea of what it is. Let me put a claim. Well, make a definition first. Definition, M1 is the modified DFA created by merging Q and Q prime, Q and Q prime in the DFA M. All right? So that's what M1 is. And then the claim is that the language accepted or recognized by M1 is the same as the language recognized by M. That after you merge two states, you have a DFA that recognizes exactly the same language that was recognized before the merge. Now, to justify this, let's just go back to this picture here. Okay? And remember that we had, I don't remember what this was, like Q7 or something, what state that was. But previously, previously we had Q prime here, okay, Q prime, and went like that, something like that. And we had Q3 that went in here, and Q11 that went into Q prime, and Q17 that went into Q prime, and so on. Now, this whole picture here, this is part of some larger DFA M. And now think about computations that go from the start state Q0 and end up somewhere, either in a final state or a not final state. But computations that start at Q0, the start state, and process a particular string W, if a computation never goes through Q prime, then what we did here in modifying the DFA has no effect. You're going to get the same computation. So if the computation starting from Q0 on the string W never went through Q prime in M, then you're going to get the same computation in M1, and it'll end up in exactly the same state that it would in M. But a computation that goes through Q prime in M, now it's altered. But think of that computation. That computation, just before it got to Q prime, had to go through Q3 or Q11 or Q17, because those are the states that point into Q prime. So that computation still goes to whichever of these three states it went to just before it went to Q prime, but now it doesn't go to Q prime. It takes the redirected edge into Q. Okay? But Q and Q prime are indistinguishable. That means that for every single string that is processed starting from Q prime that ends up in a final state, that same string, when started from Q, will end up in a final state. And every string, when started from Q prime, that ends up in a non-final state, will end up in a non-final state when started from Q. That's what it means for Q and Q prime to be indistinguishable. Okay? There is no string, put it another way, or in terms of the more original definition that we gave here, there's no string that such that when you start at Q prime, you end up in a final state, but when you start in Q, you don't end up in a final state. And conversely, there's no string Q prime such that when you start no string such that when you start at Q prime, you end up in a non-final state, but when you start at Q, you end up in a final state. What this means is that for every string W, for every string that you process in the merged DFA M1, that string will end up in a final state in M1 if and only if it ended up in a final state in M. And this means that the language that was accepted, the language that's recognized by M, and the language that's recognized by M1 are exactly the same. So this is a key point. I've given you that justification in this particular picture. You can try to write down a more general expression of that. But we have proven effectively through what I was just saying that the language accepted or recognized by M1 is the language recognized by M. With that, after having done that one merge operation. Let's look over here, see what we have. Somewhere in my notes I have noted two indistinguishable states, and what are they? We already know that A and B are distinguishable. What is indistinguishable? A and E are indistinguishable, according to my notes. Now, I mentioned earlier it's harder to establish that two states are indistinguishable because you have to argue that no matter what strings are processed, starting from one state or the other, you end up in a final state if you start from one, if and only if you end up in this final state if you start from the other. So let's take A and E just as an example. From A and E, states A and E, let's just look at the string 0, 1, 0, 0, 1, 0. I'm claiming that A and E are indistinguishable, so once we follow 0, 1, 0, from A, we should end up in a final state if and only if you end up in a final state starting from E. So 0, 1, 0, non-final. Start from E. start from E. Where's the 0 from E? Did something wrong. Well, that's embarrassing. This was supposed to be a 0. Okay. Starting from E, we have 0, 1, 0. It actually turns out to be the same state, but that isn't necessary for the definition. All the definition requires is that starting from here and starting from here, on any string, we get to a final state if and only if, starting from A, we get to a final state starting from A, if and only if we get to a final state starting from E. Okay, and of course this was just one example. To actually show that two states are indistinguishable, you would have to show that kind of behavior for every possible string. So we can't do it by just enumeration. This was just a little sort of sanity check. Did we immediately see a contradiction to the claim that A and E are indistinguishable? But I'm telling you A and E are indistinguishable. So in fact, we could have been, the merging operation, let's take A to be Q and E to be Q prime, then what that merge operation would do is the edges into Q prime, this one, would be rerouted into A, and then we would just erase Q prime. I don't want to do that in this example because I want to use the original DFA in the example to come. Oh, one more thing I should have said at the very, very beginning. The first way that you can clean up a DFA, the first way that you can reduce the number of states, is if you have any state, for example, D, that's not reachable from the start state. Here's the start state. D isn't reachable from the start state because there are no in-edges. You can see that here. So clearly, this DFA doesn't need D because there's no computation that can ever go through D. So that is a cleanup that you can do initially. Any state that's not reachable from the start state can certainly be thrown away. And so we'll just assume that that's always the first thing that's done, and that has been done in this example. Okay. So this was the key point that we got to a minute ago, how we merge two indistinguishable states, and we have LM1 equals LM. Well, having merged two states, and with this fact, if we again see that two states are indistinguishable, we can merge them. And again know that the language recognized by the modified DFA is going to be the same language as was recognized just before that step, which is the same language that was recognized by the original DFA. So we can keep doing these mergings as long as mergings are possible. We start out with a certain number, a finite number of states, and when we merge, we're obviously going to one fewer states, so we can't merge forever. So this successive merging operations is going to end at some point. But whenever you see two states that are indistinguishable, you can merge them and ultimately get down to a DFA where no pair of states are indistinguishable. Every pair of states are distinguishable. Okay, so let me write that. They can be merged together. And we can continue, to merge states as long as there are two indistinguishable states indistinguishable states. So we get a succession of DFAs with smaller number of states. We start out with the original DFA M. We merge once, we get an M1. We merge again, we get an M2. Merge again, if possible, M3, and so on. Ultimately, we get down to some DFA, which I'll call M with an arrow over it. Why an arrow? Just because that's a typesetting notation that I know how to make nicely. It comes out well. We have a DFA that has no further indistinguishable pairs of states. So this one, in M arrow, all pairs of states are distinguishable. Okay? And of course that has to happen ultimately, as I was saying. Every time you merge two states, you get one fewer state, and we start with a finite number. We can't go to negative, so of course, ultimately this procedure stops. Well, the claim that we've already established, if you apply it transitively, the language accepted by M is the same as the language accepted by M1, which is the same as the language accepted or recognized by M2, et cetera, all the way down. So we have that conclusion. That when you successively do these merges, you end up with a finite state machine, DFA, that recognizes exactly the same language that you started with. Okay. Now I want to give a name to this, this property. If a DFA has no pairs of states that can be merged, if it has no pair of states that are indistinguishable, then that DFA is called reduced. Okay, so just put that definition over here. A DFA that has no pair of indistinguishable states is called reduced. And this procedure of successively finding indistinguishable pairs and merging them, that is called the reduction procedure. So the procedure that creates M, from M it goes to M arrow, is the reduction procedure. Okay, so that defines an algorithm, but I haven't shown you how to efficiently implement. It's even more than implementation. How do you recognize that two states are indistinguishable? To recognize that they're distinguishable, you just have to come up with some string which distinguishes those two states. But how do you recognize that two strings are indistinguishable? And that's what you need to do in this reduction procedure. Well, we'll get to that. Okay? But if you can recognize that two states are indistinguishable, then this merging and creating of M arrow is pretty straightforward, what it means logically to do that. And what I claim and what we'll prove is that M arrow, this DFA, is in fact the DFA that has the minimum number of states of any DFA that recognizes the same language that it does. Okay, so I'll write that up. Maybe I should go over here. So this is the main theorem that we're going to end up proving, and we'll prove it by, in proving it, we're going to get more details of how we'll actually recognize two states that are indistinguishable. Okay, theorem. The DFA M tilde, which was created from some DFA M, okay, is the smallest, and by smallest I mean number of states, DFA such that LM equals LM. Well, let me write that in a somewhat different way. It's the smallest DFA that recognizes LM. Okay? So any DFA that recognizes the same language as M will have as many states as M arrow has. And strengthening this a little bit, M arrow can be or will be obtained using the reduction procedure from any DFA M prime such that LM prime equals LM. So what this is saying is it doesn't matter what DFA you start from, whatever language it recognizes when you use the reduction procedure, you'll end up with M arrow. And if you start with a different DFA that recognizes the same, let's say you start with M prime, that recognizes the same language, LM, when you apply the reduction procedure to it, to M prime, you will also end up with M arrow. So let me just do a little picture of this. Here we have a DFA M prime. Here we have a DFA M. And it happens that LM equals LM prime. These are two DFAs that recognize some particular language, but it's the same language. And then you do the reduction procedure on LM prime and on M prime, and you end up with something, M arrow. Or you do the reduction procedure on M, and you end up with something. It's going to be the same M arrow. That's what I have to prove to you. And this is what I'm claiming. That's the main theorem, that the M arrow that's created by using the reduction procedure from M is the smallest DFA that recognizes L of M. And if you were to use the reduction procedure starting from some other DFA M prime, where L of M prime is equal to L of M, you'll also get M arrow. And so this has an implication here, which is that the smallest DFA that recognizes LM is unique. There's only one. And that really is what this picture is showing you. If you have two DFAs that recognize the same language, and you do the reduction procedure starting from either one of them, you're going to get to the same DFA, M arrow. And this is the DFA that minimizes the number of states over all DFAs that recognize LM prime and all DFAs that recognize LM. But since LM and LM prime are the same, then we get this uniqueness. Okay? There's only one DFA that minimizes the number of states for that. Okay, so I'm going to prove that. And then later I'm going to get to the question of how do we recognize that two states are indistinguishable and how we do that. Okay. Okay, so in order to prove this particular theorem, I'm going to say it in somewhat a different way. Okay. Somewhat different way. Okay, so theorem. Let R and R prime be two reduced DFAs where LR equals LR prime. Then R and R prime are identical except for the names you might use for the names that are used for the states. Because you can have two. You can take a DFA and then just rename all of its states. What was Q1, now you'll call Q7. What was Q7, you'll call Q13, whatever. You end up with something which looks the same as a digraph, as a directed graph. But the names of the states are different. But essentially, these are the same digraphs and the same DFAs. And there's a technical term for that R and R prime are isomorphic. They're identical, even including the edge labels. So, but you'll see this a little bit more precisely. They're directed, are isomorphic as directed edge labeled graphs. Okay, well that's the theorem we're going to prove, and this will imply this over here. Because reduced, remember what reduced is? Reduced is that that DFA has no pair of states that can be merged. It has no pair of states that are indistinguishable. Okay, so when you start with a DFA that's not reduced and you run the reduction procedure, you end up with a reduced DFA. So you would end up, well, let's say with R or R prime. And this is saying that whatever DFA you end up with, if it's reduced, which is in fact what happens at the end of a reduction procedure, you end up with a reduced DFA. And we know that if LR equals LR prime, then R and R prime are identical except for the names that are used. So this is what I'm going to prove, and I'm saying this will imply that, the uniqueness of the DFA that minimizes the reduced DFA does minimize, because any other reduced DFA is identical or isomorphic to it. Okay. So actually, yeah, before I do this proof, let me just say a little bit more about why Theorem 1 is implied by Theorem 2. Theorem 1 Theorem 2. Just like Dr. Seuss, thing 1 and thing 2. Okay. So what I was just saying was note that Theorem 2 implies Theorem 1. And the main thing to realize, to go from here to here, is that the following thing. Observe that if a DFA M minimizes the number of states over all DFAs that recognize that same language, okay, then M must be reduced. It must be a reduced DFA because it's a DFA that minimizes the number of states. If it wasn't reduced, you could take two states and merge them, obtaining another DFA with a fewer number of states that accepts the same or recognizes the same language. So the DFA that minimizes the number of, or a DFA, because we don't know it's unique at this point, we're proving that it's unique, but a DFA that minimizes the number of states has to be reduced. Okay, well, this is saying that any two reduced DFAs that accept the same language are identical, which means that there's really only one DFA that minimizes the number of states over all DFAs that accept that particular language. Okay, that's that. And we know that the reduction procedure produces a reduced DFA and it maintains the property that the language that that reduced DFA recognizes the same as the originating DFA. Produces a DFA M bar such that L M arrow equals LM. Okay? So this first part says that the DFA that minimizes the number of states must be reduced. You apply this, and therefore there's only one that that minimizes the number of states. And since we know that the reduction procedure produces a reduced DFA, then we get this one as well. That what comes out of the reduction procedure, M arrow, is in fact the DFA, the unique DFA that minimizes the number of states. Okay. So this theorem is equivalent to that theorem, but we still haven't proven Theorem 2. We need to prove Theorem 2. And then I still need to tell you how to find efficiently whether two states are indistinguishable or not. Okay. Proof of Theorem 2. Okay. Well, in order to do that, to start doing that, I want to extend our notion of what it means to be indistinguishable. Our definition of indistinguishable applied to a single DFA. Two states in a single DFA were indistinguishable if there was no string which on one of those states, if we started the computation in one of those states, it led to a final state, whereas if we started the computation in the other state, it led to a non-final state. That's what it meant for two states to be indistinguishable. There was no such string that did that distinguishing in that single DFA. But now we want to talk about two states being distinguishable or indistinguishable that are in two different DFAs. So extend the notion of indistinguishability to a pair of states, Q, Q prime, where Q is in the one DFA R and Q prime is in R prime. Okay? Well, what will it mean for them to be indistinguishable? It means that for every string W in sigma star, computation, or the computation from Q on W in R leads to an accept state, or final state, whatever you want to call it, accept or final state in R if and only if, very tiresome to write this, but it's easy to say it, and I think you'll get the idea in a picture in a minute. If and only if the computation from Q prime in R on W, string W, leads to a final state or accept state. Okay? So that's what it means for two states to be indistinguishable, even though one is in one finite state machine and one is in another finite state machine. This definition. So maybe draw a little picture to make that. We have theorem 1, theorem 2. We've used up all of our boards. I want all of them. I don't want to erase any of these. So what can I do about that? Which one should I sacrifice? Well, we're proving theorem 2, and we've already argued that theorem 2 proves the main result, and so I better leave alive theorem 2. Okay. So where were we? Over here? Oh yeah, I wanted to make a picture that describes that definition, which we were just saying that here we have R, here we have R prime. These are two different finite state machines, DFAs. And here we have a state Q in R, and here we have a state Q prime in R prime. And whatever string W we have will go from Q on W to a final state in R if and only if so we go from Q on W to a final in R if and only if we can go from Q prime on the same W to a final state in R prime. And this is for each R, and for each W. Okay. So this is a little picture of what that definition says, okay, so I'm trying to prove that that R and R prime are identical on the assumption that the two they're both reduced DFAs and they accept the same language, recognize the same language. I'm trying to show that they're identical. And in order to show that they're identical, I want to show a correspondence between states in R and states in R prime, and edges in R and edges in R prime. We're going to go through and say, this state in R corresponds to this state in R prime, and this edge in R corresponds to this edge in R prime, and show that the structure of those two finite state machines are in fact identical. Okay? And it will be done by finding pairs of states in the two different finite state machines that are indistinguishable. Okay, so all right. To start that, so in proving this theorem, we've already observed that theorem 2 implies theorem 1, so we can erase that board. So to prove theorem 2, I want to demonstrate or show you a one-to-one mapping of states in R and R prime, and a one-to-one mapping of edges in R and R prime. And that one-to-one mapping has to show exactly how those two finite state machines, R and R prime, are identical. Okay. So to start that mapping, we're going to map the start state Q0 in R to the start state Q0 prime in R prime. And we claim that those two states are indistinguishable. Indistinguishable in our definition of what it means for a pair of states from two different machines to be indistinguishable. Claim Q0 and Q0 prime are indistinguishable. Why is that true? Why is it true that the start state in R is indistinguishable from the start state in R prime? Anybody answer that? What? Right. Okay, I don't know if anybody heard that on the video, so I'll repeat that. What it means for two states to be indistinguishable is that for every W, for every string W that you start in Q0 in R, that will lead to a final state or an accept state in R if and only if the same is true when you start in Q0 prime, the start state for R prime on W. Well, that has to be true because these two machines, R and R prime, recognize or accept exactly the same language. So you can't have a string which in one machine the computation runs to a final state, but in the other machine on that same string it runs to a non-final state, because then that string would be accepted in one machine and not accepted in the other machine, which would mean that the two machines accept different languages. So if the two machines accept the same languages, then Q0 and Q0 prime must be indistinguishable. A claim, I'll just write down in short, because LR equals LR prime. The two machines accept the same state. So the same language. So I'm going to map Q0 to Q0 prime. And then the mapping that we're looking for will always be mapping one state to an indistinguishable state, one state in one machine to an indistinguishable state in another one. And we've just begun that by that little step there. Okay. Okay. So here we have Q0, and here we have Q0 prime. This is an R, and this is an R prime. And now I want to show you with the mapping of edges, the edges that go from Q0, out of Q0, and the edges that go out of Q0 prime. And I want to show you how to map those. Because again, in order to show that R and R prime are identical, I'm going to show you a mapping between states of R and R prime and a mapping between edges of R and R prime, which preserves the structure, makes it clear that those two different DFAs are in fact identical. So here we started with this mapping of states, but I want to show you that, we'll see in a minute how I'm going to map the edges. Okay. So let's look at a character C. Now, the example we've been giving has just as a binary alphabet, and I've been simplifying a lot of the arguments just to the binary case. But in general, we could have a character C here without really specifying what the alphabet is. And since we know that in a DFA, there has to be an edge for every character out of every state. So this one goes over to Q1, and this one goes to Q1 prime. All right? Now I claim that Q1 and Q1 prime are indistinguishable. Well, we know that Q0 and Q0 prime are indistinguishable. What would happen if Q1 and Q1 prime were distinguishable? That means that if they were distinguishable, if Q1 and Q1 prime are distinguishable, then there is some W such that the computation from Q1 on W goes to a final, and the computation from Q1 prime on W goes to a non-final. That's what it means to be distinguishable. Of course, it may be that on W this goes to a non-final and this goes to a final, but all right. That's what it would mean for Q1 and Q1 prime to be distinguishable. But if that was true, then take the string CW. Well, starting from Q0, this would go to a final on CW. But starting from Q0 prime on CW, it would go to a non-final. That would mean that Q0 and Q0 prime were distinguishable. We've already proven that they're indistinguishable, and so we can conclude that Q1 and Q1 prime are indistinguishable. Okay? So Q1 and Q1 prime are indistinguishable. All right. So whatever state gets you, when you start at Q0 and go out on a character C, you get to state Q1, and whatever state you get to from Q0 prime on C, Q1 prime, these are going to be indistinguishable. Okay? But I still haven't shown you exactly how to map these edges. It's tempting to say now we're just going to map these edges. But I haven't completely finished that argument. Now suppose there's another character, D, that takes you from Q0 to Q1. I claim that D must also take you from Q0 prime to Q1 prime. So if we have D that takes you from Q0 to Q1, then we must have that. Well, suppose not. Suppose that on D, we got over to here, Q double prime. Okay? It was a different state than Q1 prime. Well, by the argument I just gave a little earlier, since Q1 goes on D to Q1, Q0 goes on D to Q1, and Q0 prime goes on D to Q1 double prime, we still have to have that Q1 is indistinguishable from Q1 double prime, because again, if these two were distinguishable, then there's some string here, W, that takes you to a final, and a string here, W, that takes you to a non-final. Okay? Which would mean that if you took dW from Q0 and dW from Q0 prime, you would get to a final and a non-final respectively, but that would show that Q0 and Q0 prime were distinguishable. But we know they're indistinguishable, so what we just said is that if we have this situation, Q1 and Q1 double prime are indistinguishable. Okay? Those are indistinguishable. Well, okay, so Q1 and Q1 double prime are indistinguishable, but we also said that Q1 and Q1 prime are indistinguishable. Okay? That was the earlier argument, because we go from Q0 on C to Q1 and Q0 prime on C to Q1 prime. That led us to the conclusion that Q1 and Q1 prime are indistinguishable. So Q1 and Q1 prime are indistinguishable. Q1 and Q1 double prime are indistinguishable. So we get the conclusion that Q1 prime and Q1 double prime are indistinguishable. But R prime was supposed to be reduced. It wasn't supposed to have any pair of states that were indistinguishable. We've come on the assumption that Q0 on D goes to this state, Q1, but Q0 on D goes to a different state, Q1 prime, than it got to on C. Q0 on both C and D go to Q1, but from Q0 prime on C and D they go to different states. From that assumption, we've gotten to the conclusion that Q1 prime and Q1 double prime are indistinguishable. But R prime is supposed to be reduced. It's not supposed to have any pair of indistinguishable states. So when you start with some assumption and you come to a contradiction, as this is, a contradiction being that we have a pair of indistinguishable states when in fact we're not supposed to have any, then you have to say your initial assumption was wrong. And so what we've proven is that Q0 on D will also go over to Q1 prime. Okay? So we have this picture. From Q0, all of the characters that bring you over to some state Q1, and maybe more, that bring you over to Q1 in R will also bring you over to Q1 prime in R prime. So now we can say we're going to map these two edges together. And we've begun now how to show that the two reduced DFAs, R and R prime, are isomorphic. This start state maps to this start state. Then we have an edge out which has some characters on it that goes to a state here. And we have a indistinguishable state in R prime and an edge with exactly the same set of characters. Now, over here we may have another one, F, W, F, A, B, C, D, E, F, G, say, over to another state. And the same arguments would then establish that we have that. Now, all we needed in order to establish that out of Q0, the edges and the labels on them were the same as what we have out of Q1 prime, well, all we needed from that was that Q0 and Q0 prime were indistinguishable, which we proved at the beginning of our proof. But now we have these two guys that are indistinguishable. And by the same argument, these two would be indistinguishable. Which means that we can keep going in this argument. We can say, what goes out of Q1 by a C, for example, over to some other new state. And over here we have a C over to some other new state. That these two will be indistinguishable. And whatever else is written on here, let's say A, B, C, D, E, F, well, let's say it gives an F there and an F there. It has to be on the same edges that, according to these two states. And I'm just saying the same argument that we gave in analyzing Q0 and its neighbors and Q0 prime and its neighbors can continue, because all that argument needed was that these two were indistinguishable. And we're getting that continuing fact that the correspondence, the mapping that we're showing, are between states that are indistinguishable. And then we're seeing the edges, how they map. And so you just keep, the proof conceptually just keeps walking through these two DFAs, R and R prime, showing the mapping, continuing to map pairs of indistinguishable states and pairs of edges that demonstrate that the structure of these two graphs is identical, even when you consider the edge labels. And that's it. That is the proof that if you start from, if you have two reduced DFAs, R and R prime, that accept the same languages, we needed this in order to, we needed the fact that they accept the same language to prove that Q0 and Q0 prime are indistinguishable states. Then R and R prime are identical, except for the naming of the states. Okay? So R and R prime are isomorphic as directed edge labeled graphs. And we did that by the successive argument starting from Q0 and Q0 prime, showing how edges in R map to identical edges in R prime with identical labels, and states in R map to indistinguishable states in R prime. And that's it for today. I still haven't shown you how to find whether states are indistinguishable or not. I have to leave that to the next lecture. So in the next lecture, we'll finish that and really look at the time for the algorithm and everything. Thank you.